let's do some examples from section 4.4 about bases. Number 5 says, show that the following matrices form a basis for M sub 2, 2, the vector space of 2 by 2 matrices. Now, a 2 by 2 matrix can be identified with a vector in R4 via this correspondence, that the matrix A, B, C, D corresponds to the vector A, B, C, D, like so. And this correspondence does preserve the vector addition and scalar multiplication structure, and so is a map of vector spaces. So here are the 4 matrices that are given, and one way to do this problem is essentially convert these matrices into elements of R4, and that's essentially what we'll do on the next page. Before getting to that, let's just proceed a little bit more naively and say that, okay, we need to show that any 2 by 2 matrix is a linear combination of these 4 matrices here, and also that is in a unique way. That's what it means to be a basis of a vector space, that any element of the vector space, in this case any 2 by 2 matrix, is a linear combination of the given matrices and also in a unique way. Okay, so first let's show that these 4 matrices are linearly independent. That means that if we start with a linear combination that equals the 0 vector, which in this case of the vector space being M22 is a 0 matrix, then these coefficients are all 0. Okay, so the equation here translates to this equation down here, equaling the 0 vector or matrix. And when we translate that equation into 4 equations corresponding to each component of the matrix. So for example, 3C1 plus C4 has to equal 0. How did I get that? Well, that's what's in the 1, 1 position of the matrix on the left-hand side of the previous slide. The second equation here comes from looking at the row 1, column 2 position of the 2 sides of the equation on the previous slide, and so forth. So then we've now got 4 equations, 4 unknowns, and we've seen that throughout the course that we just convert all this into a matrix, and 3, 6, 3, negative 6 is the first column. And if you look at the matrix V1, that was exactly 3, 6, 3, minus 6. And so what we were doing earlier about converting a matrix to a 4-tuple is eventually what we end up with anyway. Okay, so we just have to see if this matrix here has non-zero determinant and is therefore invertible. What we can do is row reduce it, or start row reducing it anyway. To get to this part, here I cleared out these elements here by subtracting or adding an appropriate multiple of this first row to it, so you get a bunch of zeros, and that allows us to compute the determinant a little bit more easily. Or we can go ahead and completely row reduce here. What I've done here is compute the determinant, and apparently it turns out to be 48, and which is non-zero, and therefore the determinant of this 4 by 4 matrix is non-zero, and therefore the 4 vectors or matrices are linearly independent. Essentially, the same argument will show that these 4 vectors also span M22, essentially because you can replace this 0 vector with an arbitrary vector and still solve the system of equations, simply because the matrix is invertible as it has non-zero determinant. Problem 8 says that show that the vectors v1, v2, v3 given by these polynomials do not form a basis of the space P2 of polynomials of degree 2 or less. So the space P2 consists of elements of the form a0 plus a1x plus a2x squared, where these numbers a0, a1, and a2 are arbitrary real numbers. And we have to show that these vectors here don't form a basis. So either they don't span it, or they're not linearly independent, or both. Now, the space of polynomials can be identified with R3 by this particular polynomial corresponding to the vector with components a0, a1, a2. So for example, this vector here corresponds to this vector in R3. This one, 1, 1, 4 corresponds to this vector, and likewise for this. And so this vector here corresponds to this vector in R3, which corresponds to this column of this matrix. And again, the columns come from the components of the given vector. We've seen that the matrix we want to cook up, its columns are the vectors in R3 in this case. Okay, so this 1, minus 7, 0, that's our third column. And we just have to check that this matrix has determinant, well, it has determinant 0 actually. And so this shows that there won't be a unique solution when the A0s, A0, A1, and A2 are all zeros, essentially because when you row reduce this matrix, you'll have a row of zeros, and so then there will be a free variable, C3 will be a free variable, and then you won't have a unique solution. In the case where all the AIs, A0, A1, and A2 are 0. Now, we also can conclude that because these three vectors are linearly dependent, they can't span R3. Now let's look at problem 10, which says that let V be the vector space spanned over R by the vectors or the functions cosine of squared of x, sine squared of x, and cosine of 2x. Show that this set is not a basis for V, and find a basis. Okay, so here's our vector space V. It's the linear combination of these three functions, and again, a basis is two things. It's got to span V, and it's got to be linearly independent. We'll see that these vectors essentially by definition span V, but they're not linearly independent. So let's check, or try to check, what linearly independent would mean. That would mean that if A times cosine squared x plus B times the vector sine squared x plus C times cosine of 2x is equal to 0, then A, B, and C would have to equal 0 if these vectors were linearly independent. Let's see that they're not. So first of all, by the trig identity cosine of 2x equals cosine squared x minus sine squared x, what we see is that we have a linear combination of these vectors, cosine squared, sine squared, and cosine 2x, such that they add up to 0, but the coefficients are not all 0. In fact, here the coefficients are the A is equal to 1, the B is equal to -1, and C is equal to also -1. So these three vectors are linearly dependent and therefore can't form a basis. Now it turns out that any two of the three will be a basis. For example, we can replace cosine of 2x by cosine squared minus sine squared, and then we have a linear combination like so becomes expressible in terms of cosine squared and sine squared. And one can show that these two vectors, cosine squared and sine squared, are linearly independent, although I won't do that here. But one way to do that is choose two specific values of x and see that any alleged linear combination that adds to 0, in fact, has to be the trivial linear combination where the coefficients here and here are 0.